Hello and welcome to Vodcast 14.6. In our final Vodcast for Chapter 14, I will overview hurricanes. Being a Midwesterner my whole life, the first thing I think of when I think of worst-case weather scenarios are tornadoes. In the Midwest, it's very common to have tornado watches and tornado warnings on a fairly regular basis during the spring and the summer months. But hurricanes are the largest and most violent storms on Earth. Tornadoes can cause devastating damage, but their effects are pretty localized. Hurricanes, on the other hand, are big enough to literally swallow multiple states. Just like tornadoes, hurricanes are intense centers of low pressure. But unlike tornadoes, which typically form over land, hurricanes will form over tropical oceans. And it's very important to note that hurricanes are characterized by intense convective activity and strong cyclonic circulation. I would now like to briefly overview some hurricane features, locations, and seasons. In order for a hurricane to be called a hurricane, it must have wind speeds greater than 74 miles per hour. If the wind speeds are less than 74 miles per hour, it's either a tropical storm or a tropical depression. Hurricanes also must exhibit rotary cyclonic circulation. And in the northern hemisphere, cyclonic circulation includes converging winds, the counterclockwise movement of air around the cyclonic center, rising air, and divergence aloft. In terms of where hurricanes originate, most form between the 5 degree and the 20 degree latitude. Hurricane wind speeds can reach 300 kilometers per hour, which is approximately 185 miles per hour. But unlike tornado winds, which will only affect an area for a short period of time because tornadoes are relatively small cyclonic storms, hurricanes can produce sustained winds that last hours and hours. It's also worth noting that hurricanes can generate 50-foot waves at sea. I'd like to turn your attention to the world map that you see on this slide. When we think hurricane season, the first thing that usually comes to mind is the Atlantic Ocean and the Gulf of Mexico, and hurricane season in that region will occur between August and October. That's when the ocean waters are at their warmest, and hurricanes feed off of warm, moist air coming off the ocean surface. The graph shown in the bottom right portion of this slide shows hurricane season for the Atlantic Basin. If we focus on the months of September and October, we see that the total number of hurricanes peaks during that time, as does the total number of hurricanes and tropical storms. Now, not all tropical storms will form hurricanes, but the take-home point here is that hurricane season will occur between August and October in this region, because that's the time in which the ocean waters have warmed to the greatest extent. I'd like to talk about two very important features of hurricanes, namely the eye wall and the eye. The eye wall occurs near the center of a hurricane, and at the eye wall we have rising air. The eye wall is also a location of intense convective activity. There are huge towering walls of cumulonimbus clouds in this region. It's also very important to know that the eye wall will have the most intense winds in the storm. Now, the eye of the hurricane is kind of a strange place. The eye occurs at the very center of the storm, and in satellite images it can look quite menacing. But in the eye, precipitation will cease and the wind speeds will decrease. If a hurricane was approaching you and you got hit by the eye wall, you'd be getting battered by incredibly strong winds and torrential rainfall. But as soon as the eye reached you, it can become strangely quiet and calm. Inside of the eye of the hurricane, air will gradually descend and it will heat by compression. And the eye is actually going to be the warmest part of the storm. I'd like to call your attention to the graph shown in the bottom right corner of this slide. This is data from the passage of Cyclone Mani, which occurred near Australia. The orange plot shown on this graph is the atmospheric pressure, and the red plot is the mean speed of the winds. The wind speeds in this graph are measured in knots, and I know that's not a familiar unit for us, but for now we're just trying to make sense of the data from a more qualitative perspective. The units for pressure in this graph are the standard units of millibars. On March 1st, Monty started to close in. We know that because the pressure started to drop pretty rapidly right around noon on that day, and as the pressure started to drop, the wind speeds picked up pretty substantially. Now what's really cool is focus in on the red graph from about 6 a.m. to 6 p.m. Over this 12-hour time frame, the winds are picking up in strength. But right around 9 or 10 o'clock or so, the wind speeds plunge from 60 knots all the way down to about 5 knots. And as those wind speeds dropped off substantially, the pressure was at an absolute minimum. Just past midnight, in the early morning hours of March 2nd, the eye of the hurricane reached this recording station. And when that eye was overhead, the wind speeds dropped to almost nothing. But as the eye passed and the other side of the eye wall arrived, the winds jumped almost instantaneously from 5 knots to 45 knots, and the atmospheric pressure started to increase as the hurricane kept moving on its way. On this slide, I'd like to focus on one specific mechanism that causes hurricane destruction, and that's what's known as a storm surge. Storm surges will produce the most devastating damage to coastlines. And a storm surge is essentially a huge dome of water that can be 40 to 50 miles wide, and they sweep across the coast where the eye makes landfall. I want you to focus in on this picture because something really interesting is happening here. You can see in this image that the eye is approaching the South Carolina coastline. But keep in mind that for any cyclonic storm, the air will move in a counterclockwise fashion. So the winds to the left of the eye are actually blowing back out to sea, and the winds to the right of the eye are blowing straight into shore. Now the hurricane's moving at a speed of 50 kilometers per hour towards land, but because the winds on the left side of the eye are blowing out to sea at 175 kilometers per hour, the net wind on the left side of the eye is 125 kilometers per hour, but it's blowing back out to sea. So there will not be a storm surge on the left side of the eye. However, on the right side of the eye, they will get hit by an incredibly powerful storm surge. The hurricane is moving towards the Carolina coastline at 50 kilometers per hour, and because of the cyclonic flow of air, the winds on the right side of the eye are directed straight into the shoreline. So if the wind speeds on the right side of the eye are 175 miles per hour directed straight at the shoreline, and the hurricane is moving towards the shoreline at 50 miles per hour, the net wind speed on the right side of the eye will be 225 kilometers per hour, directed straight at the Carolina coastline. On the coastline just to the right side of this eye, they will get hit by extremely powerful winds, they'll experience inland flooding, and there will be torrential rainfall. So the key concept to keep in mind when we talk about storm surges is, in the northern hemisphere, the storm surge is always most intense on the right side of the eye, because this is where the winds will be blowing towards the shore. The final consideration in this vodcast are the ways in which hurricanes can lose strength. There are three primary ways that hurricane strength can diminish. The first of which is if the hurricane moves over cooler ocean water. When a hurricane reaches cooler waters, it can't quote-unquote feed as efficiently. So generally speaking, as hurricanes move their way towards higher latitudes, their strength will tend to diminish. The other way hurricanes lose strength is when they hit land. Keep in mind that hurricanes are fueled by warm, moist air sucked off of the surface of the ocean. But once hurricanes hit land, they lose their source of energy. So it's very important to note that when hurricanes make landfall, there will be a lack of warm, moist air, and at that point, the well-organized cyclonic structure of the storm will break down. The third and final way that hurricane strength can diminish is if the large-scale flow aloft is unfavorable. If divergence aloft isn't keeping up with convergence at the surface, the cyclonic center will be compromised and the hurricane's strength will diminish. Okay, that concludes this video podcast, and that concludes Chapter 14. I hope that these vodcasts have helped you develop a better understanding of weather patterns and severe weather.